I'm Nick Barnes. I'm at NICTA, which is mostly across the road, just across from the music school. So we're you've probably heard enough of what NICTA is. Do I need to say what it is again? Okay, I'll stop doing automatic pilot and I'll start talking. So I'm going to talk about bionic eye and our work towards bionic eye. There's going to be some computer science parts to this, but more allusions to where they are, because it's going to take me most of what I fitted into half an hour, because I thought that was about the right amount of time, because I thought that was what the slot I was in, to give you the context of what vision processing for the bionic eye is about, give you the context of neurostimulation and those sorts of things. So I'll try and give you that and try and give you a picture of where computer vision and computer science fits into this, and some of the work we're doing and some of the open problems and some of the work we're doing in computer vision that fits all within that. So sensory neurostimulation has a long and occasionally not terribly proud history. There are some rather famous names. So the first person was Charles Leroy in 1750, who took this rather attractive device on the end and put electric stimulation through the eye of a blind man, and led to the person actually seeing some stimulation, so seeing some light spots. He had the idea that this would somehow magically cure the blindness, which it didn't, but the person did see something. It was about 1800 when Alexander Balto, who brought the battery to Western society and gave his name to the bolt, did something that I would highly recommend you don't try at home. He put a 50-volt loop through his ears, and what he described was hearing a kind of crackling of some paste or tenacious matter had been boiling. I include his entire lifespan in this, and that for none of the other people, just to point out he did go on and live another 30 years after he did this experiment. But I wouldn't suggest you try it. So that was, again, this evidence that you can get neurostimulation. And Arsenville introduced this term of phosphenes well, it was one of the first uses of this word phosphenes in 1896, 100 years later. So he tried putting an electric coil near other people's heads, not blind people, just general participants, not himself. And he introduced feelings of vertigo in them by doing this, which is interesting, but he also introduced phosphene. So a phosphene is this spot of light. So he used this word phosphene. So technically a phosphene is a spot of light where there's no actual light to trigger it off. And so you can induce phosphenes by electricity. You can induce it by pushing yourself on the side of the eye. You can induce a spot which is something along the lines. And of course, neurostimulation is now widely used. I mean, there's a lot of people with cochlear implants, and the basic technology that we're using in bionic eye is roughly the same. I'm part of a national consortium called Bionic Vision Australia, which is across Melbourne, Sydney and Canberra, with a whole bunch of people. So this includes surgeons, eye specialists, chip specialists, people who do preclinical testing with animals, and a whole array of people in there. Of that, there is one part that's focused on computer vision and how you do vision processing, and that's my group in Canberra. So to give you a sense of sensory neurostimulation, the basic idea is you have, in normal brain activity, you have a neuron, and the neuron has a membrane across it. And in normal brain activity, you've got other neurons firing, and they're bringing basically current via ion channels to the edge of a neuron, to the body of a neuron, and they induce via that a potential difference across the membrane of the neuron. And that leads to the neuron, when that goes up above a threshold, that leads to the neuron firing and a cascade of other neurons firing through the system, which is the normal kind of brain activity. In neurostimulation, the idea is you take something like this, which is a model, a simulated image of the University of New South Wales array, which is one of the groups within Bionic Vision Australia, and you can induce a local current field on that just by having an electric field on it, having either doing that through a combination of electrodes or one electrode putting in current and then dragging it back out again. And that in the same way can induce a local current field, can induce a current field and a potential drop across the membrane of cell bodies, and it leads to those bodies firing and the cascade through the system. Now, the difference here probably is the size of these things in comparison with normal neurons. So if you've got a normal neuron and axon, these things are tiny, they're at a nanoscale. Whereas electrodes at the moment, because you need a certain amount of, if you've got an electrode and there's a neuron somewhat close to it, you need a certain amount of power, a certain amount of potential difference across that neuron to make it fire. The potential difference that you get is inversely proportional to distance, or square law from distance. So you start to need fairly large amounts of power as you get further away, and the size of, basically the impedance of an electrode goes up greatly as it gets very, very small. So there's limitations on the size. So therefore the size of these things currently is quite large, meaning that one single electrode is stimulating hundreds or perhaps thousands of actual neurons. And this is the case in all of the technologies so far. So in Cochlear, the current implants have around 22 electrodes, whereas there are something like 330,000 auditory ganglion cells. And in the retina, we've got current arrays of sort of 20 to 100, and the highest is about 1,500 electrodes versus 1.5 million ganglion cells in the human retina. So these fields are huge, and they're leading to triggering off lots of events, and that probably explains a little what people see, which is why I'm trying to give you this physical sense of what's going on. So to give you some context, so this is just a basic patient diagram where you've got a camera resident on a pair of glasses at the front. You've got some sort of processor. Eventually that processor will be an embedded chip, probably in glasses or whatever. For the moment it's actually a laptop sitting on the side of the lap. And you've got a wireless link coming through. So you've got a wireless link that goes across the skin gap. And then implanted within the eye, and I'll give you more pictures of this later, is an actual electrode array that's doing the stimulation. That leads to activation of the neural pathways and the projection of images in the cortex. So for us, where vision processing sits is between the camera and the electrode. So our primary concern is, what do we have to do to incoming images and incoming image stream to make a person see things and use those things effectively with what electrodes they have and what stimulus we can get out, so with those phosphenes. So retinal implants or visual prosthetics so far. So these are just a few of the more modern electrically stimulating visual prosthetics. So in the 60s, Brindley and Lewin came up with this cortical device, which is basically over the back of the visual cortex. So they had a number of about 100 separate electrodes on the cortex and were stimulating directly. Within Australia, the Monash Vision Group is also taking this approach. So they're doing a cortical electrode. There's a couple of those worldwide who are trying for this sort of cortical work. in general, there's a lot more processing done by the time vision gets to the cortex, so it's more complex. And it's also brain surgery, so there's a greater complexity to the surgery. But on the other hand, there are more retinal diseases that have affected vision to that point. So in some ways, there are advantages and disadvantages to cortical implants. They'll treat a wider range of problems, but there's a greater complexity in doing them and a greater surgical risk. This particularly gruesome-looking device at the bottom here is an optic nerve penetrating array developed by CSight, the group in China. So this is to go in through the optic nerve. The optic nerve is the part that comes out of the back of the eye, which basically maps all of your retina through to the rest of the brain. So the optic nerve penetrating array allows you, when you've got complete retinal degeneration, to do something. So there's been a couple of trials. There's been only one trial with this actually stimulating, which was by a Belgian group who put 4 electrodes around the actual optic nerve and stimulated directly. And so all of these approaches, people have seen, phosphenes have had this sort of experience. But a lot of what is done today concerns retinal implants. So in the retina, so you have the eye, there's light coming through the front of the eye, through the pupil. It goes back, focus through that. Something else? No. Back onto the retina. So the retina's at the back of the eye. Behind the retina is the choroid, which is the major blood flow to the eye. Then there's the sclera, which is the white puffy material that you have around your eye, white fatty material. So there are a number of ways you can stimulate a retina. You can stimulate it from the front, which is called epiretinal. So the Second Sight Medical Products Group sticks an electrode using a thing called a retinal tack. If any doctor ever tells you you're going to need a retinal tack, you're in trouble. So it's held to the back of the retina itself, or to the front of the retina. The retina itself is an odd device in that the photocells are at the back of the retina. The photocells flow through to bipolar cells, which encode 2 to 1. So one bipolar cell encodes a photoreceptor going up, another bipolar cell encodes that going down, hence bipolar. And those flow through at the back. Sorry, I keep moving my mouse. To the retinal ganglion cells, which are kind of the main processing cells here that do some sort of grouping of field. And then from there, the axons of the retinal ganglion cells form the optic nerve and go back through the rest of the vision system and the cortex. Of the approaches, you can either go epiretinal, sticking on the front, subretinal, sticking under the retina at the back, and that's the approach being taken by a German group in Tübingen. Or you can also go suprachoroidal, so behind the choroid in the sclera. So this is BVA's first device. So this is implanted in 3 patients in Melbourne at the moment. I'll refer to those patients as 3 patients along the way, but you will actually see some videos of them. Their names are in the press, but we're not allowed to refer to people individually in what we're doing. So I'll keep it generic in my talking. I won't, for instance, say whose this picture is. So this electrode array was this is a 24-channel device. So there's a very small number of electrodes here. Currently, the Second Sight Medical Products Group has 60 electrodes, but perhaps BVA is getting better connectivity. The main reason that we're going for a low number of electrodes first as a scientific device, we're doing something that's more flexible so that we can try out more different methods of stimulation, because we're the first group. I lost my connection. No, it's still working. Oh, okay. Sorry. So we're the first group to really try out this suprachoroidal technique. So sorry, the suprachoroidal, here's an OCT image. So this is optical optical coherence tomography. So it's going through the sclera. So this is inserted into the white fatty material at the back of the eye. The actual choroid is sitting just above it, and then the retina behind that. So you're getting stimulation through the back. The advantage of this placement is that the electrode's very stable, so it doesn't move around as the eye moves around, which probably leads to more stable stimulation. I say probably because to make that statement categorically, we have to have the scientific evidence, and we're in the stages of the trials at the moment, so I can't say completely. So to give you an idea of size here, this is the electrode. So this is a retinal fundus. This is a fundus image. So you put a camera in front of the eye and you use the lens itself to focus that camera on the retina. Does that make sense? So using a fundus image, you get a very clear picture of the retina itself, and you can see the size of these electrodes compared with the eye. They're absolutely huge compared with what... I mean, if I'm going to pack 1.5 million ganglion cells in there, then there's got to be a lot triggered by a single electrode here. Okay, so there were 3 patients implanted in the latter part of 2012, and we're working with those patients now. I'm hoping this will come through in a minute. Okay, I don't know why that was holding up. So, what do patients see? So this is the collected drawings from patients. So one of the great difficulties with doing vision processing for a bionic eye is you can't actually see what the patients see. You can ask them, but all people are renownedly bad at describing what they're doing mentally. So you're able to describe what you're thinking about, but to do that to a really precise level of detail is actually really hard. And having people who haven't seen in 20 or 25 years before drawing is not actually so simple either. So these patients are drawn. So these are, the top row you see here are from the BVA patients. So basically what people get out of this is they see spots of light. And that roughly corresponds with, you're seeing a whole bunch of, you've got an electrode that's activating a whole bunch of neurons in a large spot, and that's going through and being seen by the eye. So there's a vision scientist, a visual neuroscientist on this project, Michael Iverson, and I said to him in about 2010, look, when you put an electrode in there, you're going to stimulate the retina, what sort of thing is going to happen? And he says, well, there's on and there's off cells in the retina. They shut each other down, so if you have an on cell, an off cell can't be on at the same time. So I would predict they're not going to see much at all. About a year or so later, he'd done a number of sort of experiments with modelling and animals and stuff, and he goes, you know what, it just maps through and they see great big spots. And that seems to be the activation. And the neurons are actually, if they look at the actual activations of individual neurons, there's whole, spots over which you're getting this sort of activation in the visual cortex. And so these are... it's not the patient's imagining this spot or then assembling it, it's sort of what's coming through. So imagine that a patient has a series of spots of light, roughly corresponding for the moment, 1 per electrode. These are what the BVA ones look like, so these are for the same electrode in 2 separate patients. This is the Tübingen group, the German group. They have a 1500 electrode array, which has photodiodes eye resident. They see roughly round spots, and the Second Sight Medical Products Group in the US see roughly round spots. But you can see that these are a few degrees across, basically. So these are quite large spots that you see corresponding with what you would expect of the largeness of the electrodes. But they are closed. It's not like a percept of a blurry thing across the whole image. There's like these spots that are modulated. And as you change the stimulation parameters of the electrode, what you do see is people seeing brighter or larger spots as well. So you have the ability to modulate. unfortunately, and here's a key restriction, only around 10. So you can do this experiment called a just noticeable difference. So if I show you, in normal vision, you do this experiment where you show a person a couple of screens in a row, and on the second screen a spot will be noticeably brighter or slightly brighter, and you ask the person, can they see it? You do this multiple times until you work out exactly how much brighter a spot has to be or how much more contrasted to be able to see it. You can do the same experiment in bionic eye. The trouble is, in bionic eye, the most ambitious reports of this are around 10 levels of just noticeable difference. So people can imagine a normal image that you see has got 256 levels that are encoded in it. There's high dynamic range cameras that have many, many, many more. Now we're down to about 10. So now we've got a really key restriction in what people are seeing. The other aspect that's a key restriction for the moment is we're seeing one phosphene per electrode. So we've got, for the BVA patients at the moment, 20 spots of light, and we can encode a few bits of information on each of them. 2 or 3 bits of information per one. So it's early days in this field, let me say that. But there are restrictions here that we can do something with that are interesting for computer vision. Okay, so vision processing can assist. It can assist with reduced spatial resolution. So we've got a reduced spatial resolution from so people have reported acuity values of about 1 cycle per degree versus 60 in normal vision. We've also don't have the ability to fixate, so normal people in normal vision, you have a fovea which is about the size of your fist at the length of your arm. Other than that, the rest of your vision is largely black and white, motion sensitive. You don't see any colour in the rest outside your fovea. And you make up this image that you see of a lecture theatre around you by fixating your fovea around and filling in the gaps and imagining that you see this coherent image. That's something that isn't there automatically in bionic eye, so that's something that we've got to deal with as well. And we've got this reduced dynamic range. So vision processing, from my point of view, what it needs to do is replace fixation, ensure that key objects are contrasted. It needs to optimise the use of the dynamic range, and it needs to offer a display that implantees can understand. So I could imagine optimising a channel like this. You know, I've got 20 separate channels. I've got 4 bits on each. I can refresh some number of cycles per second. I mean, just do JPEG and send it through. Probably won't help. So fixation first. So we can do fixation. So we can do a fixation-like mechanism by doing face detection in the image. So here we've got Xu Ming's face moving around the stage, around the area, and we can take, so that's a 32 by 32 image of that scene. So 32 by 32 is the end goal of BVA, to have an electrode array that's at that size. If I render that whole scene at 32 by 32, you could roughly tell that's a person, but not much more. Whereas if I zoom in on Xu Ming's face here, then you can see it. And the image to the side there is called a simulated prosthetic vision. So the image. So the idea here is to reduce it to the kind of things that people report seeing, the phosphenes, and the number of levels that they're seeing, and see how well people can see those and see how it looks. The idea being, if we can encode the sort of information that people are seeing, we can trial that with normally sighted people and see if they're able to actually recognise things. I'll come back to that. So what's under the hood here is fairly simple. You've got a straight face detector going on. You do a distance transform. So I take an edge map from the previous frame, I take an edge map from this frame, and I work out how much things have moved in between. I have the previous frame to know where the face was in that. I've assumed that I've detected it. And I basically look at a similarity matching and I try to keep things moving smoothly over time, keeping the edges of the faces. So I could just do something like a face detector in each image, but face detectors in computer vision just detect whether there's a face there or not at a template. They're not very good at getting accurately the boundaries or landmarks within that face. So this is something we're able to do real time, merging those two in a tracking procedure that will hold the face still. And this is what Sandra Bullock looks like through that whether I should expose it, if it's aimed at bullet or not. I'll leave it up to you. So, if you see the whole scene, it's very hard to recognise, but if you stay fixated on a face via this, then you can get a good understanding of what she's doing. And particularly, you know, video helps. Seeing someone move through in a limited resolution really helps you. But let's see how much it does or doesn't help. So I'm going to do a trial on here. We have a concept of informed consenting trial, so feel free to not participate if you want to. And I'm not going to record data, so it's fine. So we want to know whether or not a vision process, so I want to evaluate whether or not a vision processing method will help patients. So I can trial that with patients. I can also take simulated prosthetic vision and I can trial it with normally sighted people. So the idea here is I have someone like Andre Agassi. I'll choose less famous people for the trials because otherwise, because people recognise people they've seen before very well. Famous people are really bad people to use in trials. So I've got a video of Andre Agassi kind of moving around doing a press conference. I've got a fixated view of him, and I can phosphonise the video moving around. I can phosphonise the face-detected version of it, and then I take a random frame out of that to get rid of the video effects and see if you can recognise it. So what we did in a set of trials was we show people 4 faces in a block. They're shown that for 20 seconds. And then they're shown a phosphonised face of this one's 16 by 16, which is a slightly closer version that we're about to do. That is the next video step after the current. We show that for 15 seconds, and then then you've got to guess. So are you ready to try? We'll have 20 seconds on this image, if PowerPoint is behaving itself. Seconds. Okay, hands up for those who are going to participate. For top left. Okay, couple. Hands up for top right. Oh. Which left are we going? Okay, so that's left. Okay. Hands up. Sorry? Right. Take our right. You're right. There's more people on this side. I suddenly worked out the problem. Okay, so this is right. Okay, so who's up for bottom left? Yes. Who's right here? It wasn't him, wasn't it? And who's up for bottom right? Okay. I'd judge that about 40%. It was bottom right. You can do much better in video versions of this. We believe we haven't tried it. But we did this with well, if you look at video versions, it's easier to solve the task than this. Formally, I can't say that because we haven't tried it. Sorry, I'm using research terms. So we did this with 10 people, 5 males, 5 females. Everyone recognised better than chance for all of the representation. So we took 4 displays. We gave them the whole scene. We let them manually fixate, so pick where the face is, zoom in, and then see the zoomed in face. We did straight detection, or we did our fixation method, and we just show them a random frame from the video as it goes along, so that if detection fails at some point, it'll fail and it won't do very well. And basically, everyone went better than average, better than chance on all of them, significantly better than chance. Manually, so fixation worked, detection worked better than full scene, fixation worked significantly better than detection. When people actually had this chance to zoom in and pick where the face was, they did quite well on that. The only trouble with that, so they did about the same as fixation. The only trouble with that is that's very slow to do, of course, and doesn't work very well in video, actually. But, so what's generally used in this field is the idea of an ease of use, where you actually look at how long it's taken to do them, and there's a standard formula for looking at this, accepted within literature. And so, of course, the fixation gives you a much better ease of use. So, 2 lessons from this. One, 16 by 16. Even though it looks hard, it's enough to do kind of okay on face recognition. And 2, fixation works, basically. So, 2 other methods that might do this. So, there's also a topic in computer vision called segmentation and sort of scene understanding as a whole. So where you try and label a set of pixels in the image as belonging to a foreground object or not. So I can imagine a scheme where I've got imagine I've got a camera and I've got an emphasis in this camera, a very low dynamic range camera, and I take whatever spot is at the centre of my field of view and I look around in the dark and try and see something, and I up the contrast of that object versus the background. So to do that, I've got to find out where this object is, and that idea is one of segmentation. So of course, if I've got very low dynamic range, if I took a standard image and just mapped it to the low dynamic range, I'd lose a lot of detail, of course, and I might lose the detail that's critical to what I'm doing. So I can segment the object which is in the centre of the field of view and highlight it. So for instance, on this particular sign, although those objects, the Chinese characters are red here, they're not very well contrasted actually in the brightness of the image. So if you put them into around 8 levels of noticeable difference, so if you encode them as 8-level phosphenes, you see nothing. But of course, if you pre-segment, it's a simple segmentation task, so you can pull text out. So segmentation can help here for signs and figures like that, and other objects potentially as well. So, briefly into computer vision mode now. So one of the things that we're interested in computer vision and in Bionic Eye is how much we can work out of a scene, how much we can pull our objects apart, how much we can find objects reliably in a scene. The particular approach that we were doing here, this was by a PhD student, Tao Wong, was to use a pure detection approach, a Huff-based detection approach, and try and find out an object and work out its occlusion mask. So after its occlusion mask, we run a standard approach of segmentation after that, a grab cut that gives you a sharp boundary of the object. And you can get these objects. So let me briefly explain this method. So the idea is to use this method called Huff voting. So there's lots of different ways of doing detection. One of the methods you can use is Huff voting. The advantage of Huff voting is it takes whatever information you have, assembles those bits of information to try and guess where the centre of the object is. So I have this idea of a visual patch. So I've got a little patch of scene somewhere, and I'll say, well, this patch might have some potential to be useful here. And I know where the object is. I've got a series of images where someone's hand traced them and they've said, this is a chair. Then what I do is I get each one of these patches in an image that I know to say, well, this patch is evidence for this chair being here. Let's see if that helps. And I do this for all of the images, or a set of patches that I determine are good patches in some way. And those patches would vote to the object centre. And I look over a whole series of images in the database and I see how many times these are useful in actually determining what's going on. I choose patches that are more relevant for predicting objects than other times. And then I've got this map where the basis of it is I have object patches, and those patches have a vector by which they're voting to the centre of the object. That's Huff voting. And then you accumulate this kind of vote centre at the centre of the image, which roughly forms Bayesian reasoning via a log likelihood map. So it's roughly it's justifiable in probability, and you get the centroid of an object. Now what we did here was generalise this method. So there's 2 aspects in which we generalised it. A standard one is you can also vote for a mask of the object. So at the same time you're voting for the centre, you take each one of these patches and you say, well, this is where I think the object would actually be on the basis that you've hand traced out the object for that scene. So I can take all of my patches that are voting for it, all vote for a mask on it, and I just take the most likely mask amongst those. But I don't have to just worry about things that are on the object. If I take something like a depth-based camera in my training phase, I can take points that are actually on the object. So I know the depth of the object because it's being hand traced, I know where it is. And I can say, well, these are in the object layer. I can take points that are occlusion layer, so points that are actually in front of the object and maybe occluding it, because I want to find out what's occluding the object, things like chairs and tables. I can take things that are close up and things that are far away. And all of those form context. So I'm taking patches across various layers of context of the object to help my assumption about it being there or not being there. You can also give negative votes, so a patch can be voting against an object's presence or for an occlusion. So I can accumulate from a single scene the votes from each of those sorts of things and from each of those distances, and I can accumulate a map. Now, once I've actually trained on that, once I've used the depth to know where those patches are, if the patches are going to be the same in similar scenes, I don't need the depth again. So I can throw away the depth of that stage and just take the knowledge of patches that are in these various layers and use those to form my detection of an object. So that idea is one of Huff-based object detection, giving us actually a mask of where the object is and trying to find those objects. So I guess that's an example of computer vision scene understanding, and so here we're just layering more and more on detection rather than doing a lot of pixel-based reasoning. But I guess this is an interesting set of computer vision questions around we can use these sorts of pixel-based reasoning methods, we can use detection. So interesting questions here are, can we make, interesting question. Can we make use of pixel-based reasoning for understanding scenes fast? That's very valid for bionic eye. You want to actually work out what's going on in a scene in the loop of someone seeing things and having enough time to process it, or having enough time to react to what's going on. So you want it within a frame. Can we make, an orthogonal question is, can we make this work on very, very large sets of images? So say it's Australian neural networks, something that NICTA is interested in, and can we make use of very large training sets? So at the moment, people tend to use training sets of around 100 images to try and work out a particular scene. Can we make use of vast numbers of objects? So we've got a database of 200 million of Australian road image cards. It's fascinating to sit there and watch the road, you won't probably know that. So can we make use of that sort of description of data to make better detectors? These are sort of research questions in computer vision. But back to the topic at hand. So now I've said what segmentation is. I'm going to give you an example of this sort of scene understanding, how it can help directly, and I'm eventually going to finish, or soon going to finish, with the patient aspect of this. So we do trials. So one of the key things that people report in focus groups being interested in is getting around. So people who have no vision at all are really motivated by being able to move around independently without someone there to assist them. That's a really important thing. People with a bit more vision are more interested in things like face detection because they can get around. But right now we're dealing with people who have no vision at all, and this is kind of a key topic for those. Unfortunately, you don't need very high resolution to do navigation. So we trial people with a full wearable simulated prosthetic vision kit. Our new one looks a little bit better than this shroud, which looks rather executionerish, I think. So we've constructed what is a maze where you can randomly move around curtains, etc. And in this particular instance, what we were interested in is low contrast objects. So if I have something like a black bin on a dark floor, how are people going to be able to see that? I mean, with the limited dynamic range, if you just map it through, obviously they're going to have a lot of trouble. So can we come up with methods that and it's going to require an intervention, it's going to require some scene understanding. So if I render this scene as raw intensity, then I don't see that object at all. So this is with 4 bits, so this is, 2 bits, so this is just 4 levels, which is realistic. I don't see that object at all. If instead I render this scene as raw depth, so I'm just wearing in this case, a Bumblebee stereo system. We're also working with Connect or those sorts of things, working doors. There's lots of good kind of depth mapping hardware devices becoming increasingly available. Even if you buy high-end Mercedes cars, you'll get them. So if I render this as depth, you can sort of see the object there, but it's not very clear. And the other thing I've lost in this depth map is the boundary of the walls become really unclear. So what I'd like to do is find the floor and just make sure the boundaries of the floor and the obstacles are high contrast. So that's exactly what we do. Eventually. Good. So we can fit a ground plane, so we can take a depth map of this environment, we can fit a ground plane, so we can find the most likely ground plane, we can use an IOU and found the downwards vector and project that on, and we'll find the most likely thing that is actually ground rather than the wall if they look up. And we can map that to itself, so the ground plane is fine. Then we can look at all the points around the ground that are not on the ground, particularly the boundary points, and just push them up, so to make them higher contrast. And so this is what it looks like. If I up the contrast of the object, I force it to stand out, and you can now see the boundary here, because I've detected, just using standard plane fitting techniques, found the ground plane inside the objects. So here we're actually using a basic scene understanding in the loop. And that does actually help. So we had a number of volunteers walking through wearing a 98 electrode simulation of this. And we looked at the time they're taking to walk through compared with their standard walking speed. And we also looked at the number of collisions that they have. And what we found was with augmented depth, this augmented display, we get around a factor of 2 reduction in their number of collisions, which you would expect because they can't see them otherwise. They can only just see them. So, but it shows that you can get methods fast enough and you can get them in the loop and they work. There's another aspect to this. So what I said in that last version was we just push the ground down or push the objects up. That's kind of a hack, right? So what I really meant by that was what I want to do is I want to enforce contrast at the boundaries of objects. I want to enforce the plane to be flat, and I want to enforce a one noticeable difference step up at the boundaries. That has a dynamic range constraint, so I want a pixel to be one level of noticeable difference greater than its neighbours when it's a boundary pixel. And otherwise I want everything to stay consistent with where it is. So I want the original mapping of what was further away stays further away. And I'm doing this in a depth-based representation. I apply that. So here's the scene going through. If I apply the ground plane constraint, you can see here that's the previous method. You can see here the floor is clear, but I've got no graduation of the floor. It's just the one depth. But if instead I now do the full optimization, you can see I've still got my contrast of objects, I've still got my objects clearly presented versus the original where the boundary was lost, but now I'm seeing I've got a bit of dynamic range left to encode the rest of the scene. So I can fit in just a straight optimization here and get a better result. So finally, to what we're doing in patients at the moment, very basic. So are people familiar with, I'll ask a series of questions, reconstruction filtering? Nyquist theory? Sorry? Shannon. Sorry? Yeah, Shannon Nyquist, yeah. Okay, so the idea of the Nyquist theorem is if I take a series, if I've got a continuous signal that I want to reconstruct, so I've got an image, and so I've got my image here, I've just taken a series of point samples of it. How do you actually have to do filtering of that image? I'm going to jump to the use of it rather than the theory. How do I actually have to apply a filter to that image to allow a person to understand what's going on in the image? It also tells me how much information I can carry through for what's going to be lost. And that basically says you apply a particular size and type of filter, which is a Nyquist filter. And so so this C is a standard low vision test. It's called a Landolt C. You'll display it in front of the patient on one angle, another angle. The patient will have to say, is it up, left, right, etc. if I display this in simulated prosthetic vision, if I just take point sampling of the image, then I can lose the C because I'm just actually sampling the pixel that is closest to the centre of the image. If instead I do a filtering of this image, then I'm not prone to these sorts of events. I'm taking an influence over a whole region of the image into what I put out as the output, and I get a thing that still shows the actual disjoint in this. And this is signal processing theory. This is an optimal filter. What we see is as we move to the filter size, which is predicted by theory, if I do these types of acuity tests with simulated prosthetic vision, at that ideal acuity, I get the best results. So Shannon and Nyquist were right about prosthetic vision about many, many years ago. And this is, I mean, that seems abstract and flippant, but in a sense it means that what we're seeing in this sort of downsampled world is that things still obey the rules of standard signal processing. You can take theory and things work as you would predict them. So we took exactly that and put it in the loop of vision processing. So we have 3 patients in Melbourne at the moment, and they're running that precise reconstruction filter. So they have these 20 fields of view that I showed you at the start, and each one of those is taking this kind of reconstruction filter, and they're trying out different trials. Here's Morris. I doubt you'll be able to hear Morris, but let's play through this anyway. No chance we can hear that, right? I'll start again.
Put a triangle somewhere on the board now, Morris, and I want you to first of all come back to the centre of that square. And after I've finished placing it, I want you to have a go exploring to the left and to the right, and above and below that square. And now I want you to come across to the right side and have a scan up and down on that right side, and tell me if you see any electrodes come on there.
And it comes across into this section of the board, and it's just dead off centre. It's coming into the side section here.
Okay, so 3 things with Morris here. You can tell with Morris because you say his name, and this is a public video. So first thing is he has a camera mounted on his forehead. There's a cable coming off that to a laptop, and that's what's going into stimulation. So it's processing live with what he's seeing. The video, the shot that you saw briefly of the screen on the side, that actually shows his activated electrodes in any single cycle. So we have a clinician's window so they can see exactly what we're stimulating to him, which is different to what he may be seeing, of course. But it seems to be there. The trial that Morris was doing here, this was one of his first actual sessions with the camera switched on. So it was very early and we were enthusiastic about this. The results are getting better and better for some of the other patients who've been in longer. But what he was able to do, I don't know if you could work this out from what he said. In this version, we were putting a triangle around one of the 4 sides of this display, and he was able to say which side it was on by seeing that there was activation on that side. So the general test that we're doing here is my last slide. Is a barn localization test. So this is a low vision test. So Morris has bare light perception, which roughly translates, if you close your eyes, you have bare light perception. So you can tell if the lights are on, but you can't see anything else. That's all Morris has had for about 25 years. So bare light perception cannot pass this test. So the test basically shows a spot in the centre and one of 4 wedges. And you have to say which one of those 4 wedges comes on. So you show a spot and then you show a wedge come on. It's a localisation test. So you've got to localise on the centre and then say which one. Morris and our other patients are actually able to pass this test now, which actually takes them out of no light perception into a category which is still quite blind, but not actually no light perception anymore. So technically, this is a pass of not completely blind now. And Morris there was doing an analogue of this test where he actually had, so for training in the first instance, we used physical objects so that he could touch them, so he could get an understanding of what his vision was seeing. But I guess the end point of all of this is we've got this prosthetic vision, we've got these problems of low resolution and dynamic range, and we've got computer vision techniques that we think can address them. What we've done is taken the most basic first kind of computer vision methods and put them in the loop with patients. So this is actual code that's written in Canberra, co-written with people in Melbourne who are doing the testing. So they're doing adult patient safety in the system and integration of what we're doing. And we're running that with patients, and it's showing improved results over the default methods that are in the literature at the moment. So I guess that means, so I've presented you this series of other methods that we're expecting to use in computer vision over the next years. And our expectation now that we didn't have about 4 weeks ago is that, yes, the vision is behaving itself at the low level. We do have a handle on how it works. And so we do expect now that these higher order methods that are using contrast and showing things in the scene have a good chance of working with patients. And that's what we'll be working towards over the next few months, basically. And that's about where we are. Thank you.
Okay, we have time for a few questions. Are they using Wi-Fi to get connection to the thing, or are they using a cable to the server?
Okay. So do you mean from the implant
from the headset that you said?
Yep.
To the data that goes through. Or the data going stored on the headset itself?
Okay, so for this particular one, this is a lab-based setup. There's nothing portable here. It's like we're doing, this is very early days in the sense that what we're trying to do is establish the chain that we need of software to make stimulation work, to work out what the parameters are and what works. The pair of glasses has a cable running off it. It's running to a laptop that's on the side. It's running to a stimulation box to stimulate the patient. In this particular case, we actually have a direct lead to the patient. There's actually a direct wires. The reason for that is scientific in this case because it allows us this. So the other groups at the moment are doing a digital connection. So you go through a non-skin gap. The problem with that is as soon as you go digital, you're limited in the number of parameters that you can stimulate. You're limited to your best guesses. Yep. And so this allows us to stimulate the whole range of parameters.
The security side where people can break in and
there's other ways of dealing with security.
So by all means, that this might be a future implementation for the thing in the industry, right? So in cochlear implants at the moment, what they use is they have an antenna on the inside, and the inside device is entirely passive. There's no battery, and you're using an antenna on the outside with a device out here to power the device and send data through to it. And that's the same sort of thing that will probably be used in these. There's also people investigating antenna technologies where you wrap a piece across the eye itself inside glasses and transmit directly to the eye. That seems to be viable for the area research and those sorts of approaches. So eventually there won't be wires across the skin gap. There was in the early cochlear days, and Cochlear are back investigating these kind of connection methods to investigate parameters, but no, it will eventually be wireless.
When you segment images or when you're segmenting a photo stream, is there any way to transmit the orientation of where you're taking that segment from? Because if you're trying to watch something closely and it moves out of the field of view from the camera, you want to know where to redirect the camera to keep tracking that object.
Correct. So there's two ways of handling it. One is, so if I'm zoomed in on your face and you're kind of moving around like Sandra Bullock was, then
I can just track that and I can say, well, that's kind of moving within screen, so I'll just keep it fixated. If she were to move too far or completely turn away, or I was to turn my vision away, then it should just go back to a zoomed out display, is the idea. And I think there's probably a fair bit of user interface finesse in getting that working nicely. I think the concept's clean, but some sort of stage kind of zooming down and control is what we're going to need.
And is there any ideas on how to transition from the broad, the zoomed out stage to the segmented stage?
To a zoomed in stage?
Yeah.
I would imagine it'd be a user selection. You couldn't do it automatically because that would be just too annoying. You'd either have to switch into a face mode where you're interested in it, or actually press a fixate on object button, or have a blink control would be another method. So something along those lines.
How far away do you think we might be from those both those two?
So, a couple of answers. So one, there's an implant in Germany by Zrenner, the Tübingen group. They're using eye-resident photodiodes. So they've actually got photodiodes on a chip in the eye. They're powering it from outside, so they've got wires outside. They actually have around 32 by 32 in that implant. At the moment, they're not getting acuity values. So when they do tests like Landau-C, etc., they're getting acuity values that are roughly the same as the second sight group with 60 electrodes. And it's very hard to tell if that's because their electrodes are too tightly packed, so they're not getting separate stimulation, or photodiodes don't focus light very well, so maybe they've got an optical blur in front of it getting nothing, or maybe a combination of those. So it's sort of there, but it's not really working in their case. So BVA is going for its first stage is a 16 by 16 because surgically there's complications as you kind of pack more space. I would hope that would be in patients in a couple of years, but you might imagine that getting something into patients has got a lot of complexities to it. And probably, well, it's got more complexities to it than we imagined at the start. So I guess I would hope 32 by 32, sort of 5 years, would be a reasonable prediction in patients. As to a commercial device that can be bought over the counter, well, no, never over the counter, bought through your local friendly eye surgeon, a bit further out. But actually, the second sight device now you can actually buy. It's not actually being a medical benefit, but you can actually get yourself implanted with one of those for only $100,000 or so.
What key technologies need to be advanced for these things to become viable over a period, like local friendly eye surgeon?
Local friendly eye surgeon, yeah.
with a relatively high visual acuity.
So I think to help people who have who have no vision at all, what you need, so I'm going to answer that functionally rather than in terms of technology. So to help someone who has no vision at all, you've got to help them get around. I think so we've done a lot of simulations with people through environments doing prosthetic vision, mobile navigation kits. I think somewhere of the order of 100 or a couple of hundred electrodes is enough to give some benefit. So some chance of getting around. We haven't done a lot of outdoor work, but people getting through corridors and stuff like that, somewhere around 100 is actually okay. That's kind of feasible in the next few years. That's not far from where BVA is at the moment, really. On the other hand, the next step up is into patients who are able to get around and want to do things like reading and recognise faces, etc. That's sort of the next category of blindness. Those are hard. So at the moment, our patients can see letters that are about this big, as can second sight patients. to do that, I think you need somewhere around the 16 by 16 or 32 by 32 to really... So we showed an effect. We showed around 60% recognition with faces with 16 by 16. If you think I was walking out in the street and I was saying, oh, hi, to some old friend that I'd seen years ago, and I was right 60% of the time, that'd be bloody annoying, right? So I probably don't want to do that. I want to get the technologies a bit better than that before I get there. So probably for the kind of face recognition, you're out around that sort of 5-year mark before we start getting those things into patients, I imagine. And to really make that effectively work, I don't know. So what are the barriers? There's a barrier of pure electrode density and making those things actually work effectively in patients. So I can produce, well, I can't. My background's computer science. I can't produce an electrode array. People within BVA and other areas can produce electrode arrays that are as dense as you like, but actually turning those into stable stimulating devices that generate the kind of percepts in patients. There's a lot to be learned still. And so how long it takes to translate to really effective vision at that layer, hard to know. So I guess there's the kind of barriers are, for me, vision processing, getting a better and better understanding of that interface and how to drive that interface between phosphenes and images, and how patients understand that interface. And then getting techniques that work to the way people want them to. So is fixation, how would you do it? What do you need to do with your dynamic range on the face to help? There's studies you could do in there. For other parts, it's how do you actually get that number of electrodes packed in, safe, stimulating? How do you reduce the power of these devices so you can fit more electrodes in? Because currently, you've got this distance gap you've got. So but basically, almost every step within it needs advances to get to that level of blindness, I guess.
Okay, I think we'll wrap up there. Thank you for giving an amazing talk. And on behalf of all of us, I'd like you to present you with the next speaker.
Oh, thank you very much. Thank you.